In this video, I'm going to pick up where I left off with the last video, which is in determining the nth term or the general form of a sequence. So in my notes, I gave you the final result, but I actually didn't show any work on how to get there. So I'm going to be doing that in the video. So when you're given a sequence, what I like to do is separate the numerator, separate the denominator. So in this first example, I look at the numerators and I see 1, 2, 3, 4, 5. Another thing I like to do is to label the n values, the domain values. So this first term corresponds to n equals 1, then n equals 2, n equals 3, 4, and 5. That gives me a clue as to the relationship between n, which is the input number, and the term of the sequence, which is the output number of the sequence. Because remember, a sequence is a function, or the inputs are the natural numbers, in this case 1, 2, 3, 4, 5, etc. And the outputs are -1/2, 2/3, -3/4, 4/5, etc. So the first thing I notice is the numerators are equivalent to the n values. So in my sequence, I know, separating the numerator from the denominator, I know that my numerator is simply n. I look at the denominator, and I notice that each one of the values in the denominator is simply one more than n. Now, I may not have noticed that the denominator was one more than n right away if I hadn't noticed that the numerator was equal to n, but then all of the denominators are just one greater. Sometimes when you figure out the numerator or the denominator, then the other term is related to it somehow, and it makes it easier to figure out. So the denominator is simply my n value plus 1. The last thing to figure out is this negative, positive, negative, positive, negativeness of the sequence. In other words, it's an alternating sequence. Every other term is negative. And I showed you how to do one of these in the previous video. So you remember that these are simply going to be some power of -1. Well, if I let this be -1 to the n, and n is equal to 1, the first term, then -1 to the first power is -1, and that's what we want. We want the first term to be negative. When n is equal to 2, we get -1 to the second power, which will be positive, and so the second term is positive, and so that's going to alternate. And so the final piece to our little puzzle here is -1 to the n. And that, of course, is our a sub n, and that was the value that I gave you right here. But that's how I figured it out. You look at the numerator, you look at the denominator, and then look at the alternating sign aspect of it. Okay, don't look at this right away. So let's take a look at the numerators. First of all, this is n equals 1, 2, 3, 4, and 5. And so clearly the numerators are not equal to n, but what is the relationship to them? Well, there's a couple of different ways that you could look at this. First of all, each one of the numerators appears to be a power of 3. That's the first thing I noticed that. I say, well, 3, 9, 27, that's 3 to the first power, 3 to the second power, 3 to the third power, etc., etc. So it looks like the numerator is simply a power of 3. So when n is equal to 1, the first numerator is 3 to the first. The second would be 3 squared. Another way of looking at that is that the numerators have a constant ratio. The numerator has a constant ratio. So the numerators themselves are a geometric sequence. The numerators are a geometric sequence. All right, so the denominator, 4, 7, 10, 13, 9, 16, they don't have any relationship to n that I can see. That's clearly evident. And so just kind of examining what is the pattern, what is the relationship. They are not powers of anything. But then I notice, just like the numerator was a geometric sequence because there was a common ratio, the denominators are an arithmetic sequence because there is a common difference between each of these numbers. 4 plus 3 is 7, plus 3 is 10, plus 3 is 13, plus 3 is 16. So I have an arithmetic sequence here, which would be in the form of a sub n is equal to a sub 1 plus d times n minus 1. That is the general form for an arithmetic sequence, where a sub 1 is the first term, which would be 4, and d is the common difference, which is 3, times n minus 1, which simplifies to 4 plus 3n minus 3, or 3n plus 1. So that's my denominator. So that would be my formula for the general form. And of course, I didn't do it with either one of these, but you can check once you get your nth term formula. Try the first few terms. Make sure that you get these terms over here. In other words, say, okay, well, what is a sub 1? A sub 1 here is 3 to the first over 3 times 1 plus 1, which of course is 3 over 4, which works. This is 3 over 4. And then figure out what a sub 2 is using your formula. And make sure that you can get these terms over here just to make sure that it works. It's like a check. And of course, you can do the same thing with this one up here. All right, the next two examples are recursively defined sequences. And so remember, a recursive sequence is a sequence where each successive term depends on the term before it. So in a recursive sequence, you have to be given the relationship between the two terms, between the term and its previous term, and that's what we have here. A sub n, which means the nth term, is negative 3 times a sub n minus 1. In plain English, what that means is that every term is equal to the previous term multiplied by negative 3. So let's just find the first few terms of the sequence. A sub 1 is given to us. That's another thing that I mentioned in the previous video. You have to be given some value. Usually it's going to be a sub 1, but it might not be. It might be a sub 2, it might be a sub 3. Usually a sub 1. So we're given a sub 1. We know what that is. That's a gimme. So a sub 2 is going to be negative 3 times a sub n minus 1. In other words, negative 3 times the previous term, which was 2. So that's negative 6. A sub 3 is negative 3 times the previous term, which is negative 6, which is 18. A sub 4 is negative 3 times 18, which is negative 54. Okay, so we now have the terms of the sequence. So we have 2, negative 6, 18, negative 54. Now up here it says we only want to consider from n is greater than or equal to 2. Well, this first term is n equals 1, so we're just going to omit that. So we're only looking at these three terms to try to come up with a pattern. Okay, we want to come up with a pattern of how this is going to work. So the general procedure that I like to use, again, is I look to see what the relationship is. I first look to see if there is some type of an arithmetic relationship, a common difference, which there is clearly not. Then I look to see if there's a geometric relationship, in other words, a common difference. Well, I notice that 18 divided by 6 is 3. 54 divided by 18 is 3. There is a common difference here. So this is a geometric relationship. This is a geometric sequence, right? And looks like I'm going to have to get rid of some of this. So the geometric sequence, remember, takes the form The geometric sequence takes the form a sub n is equal to a sub 1 r to the n minus 1. So the first term in the sequence is a sub 1 is 2. So a sub n is 2. And then my common ratio is 3 to the n minus 1. Well, that would be great if it wasn't for the alternating negatives. We have a negative, positive, negative, and that relationship will continue. So once again, we have to put in a power of negative 1. And so if we have negative 1 to the n, well, when n, we're starting with n equals 2. When n is 2, we get negative 1 squared is a positive 1. Well, we want a negative here. We want the first term here to be negative, not positive. So I'm going to try minus 1. So negative 1 raised to the n equals 2 power minus 1 is negative 1 to the first, which is negative. All right, so I'm going to continue down here. So we have a sub n is equal to a negative 1 to the n minus 1 times 2 times 3 to the n minus 1 power. But we can combine this term and this term. Just like if I have x squared times y squared, I can write that as xy multiplied together to the second power. I can take these two terms and write them as 1. So I'll write 2 times negative 1 times 3 is negative 3 raised to the n minus 1 power. And there we have our sequence. Now, you can check this by plugging in values of n starting at n equals 2. When n equals 2, we have 2 times negative 3 to the 2 minus 1 is 1. Negative 3 to the first is negative 3 times 2 is negative 6. And that gives us this first term here. And so we can continue checking those. Now notice that if it didn't say from n equals greater than or equal to 2, this first term was not going to, did not have the same relationship, did not have the same common ratio. Actually, yes, it did. I'm sorry. It did have the common ratio. But we still wanted to start it from n is greater than or equal to 2. Yeah, because that was a 2. Sorry about that. All right, one more. Oh, nope. I'm writing in the space of the last one. So let's get rid of all this. Once again, I needed to allocate a little more space in my notes. I'll rewrite these someday and put some more space in here. Okay, so let's go through this same process. This is another recursive sequence. So we're given a sub 1 is 1/2. A sub 2 is now a sub n minus 1 plus 1/2 to the n. So that's going to be 1/2 plus 1/2 squared is 1/2 plus 1/4, which getting a common denominator is going to be 3/4. A sub 3 is going to be 3/4, the term before it, plus 1/2 cubed, which is 3/4 plus 1/8, which is 7/8. And a sub 4 is going to be 7/8 plus 1/2 to the 4th power, which is 7/8 plus 1/16, which is 15/16. All right, so that's good enough. So writing out the terms of the sequence, we have 1/2, 3/4, 7/8, 15/16. 16ths. And again, don't look at that. So this is from n equals 1, n equals 2, n equals 3, n equals 4. Now, looking at the numerator, it's very hard to figure out what kind of a relationship there is in that numerator. So I'm going to go and see what I can dig up with the denominator. Sometimes you have to look at the denominator first. And I see 2, 4, 8, 16. Okay. Well, that looks like it could be there's number one, there's a common ratio. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So it looks like it's geometric. But also to aid me in that, I notice that each one of them is 2 raised to the n power. All right. And so if we just take a look at the geometric idea, their common ratio is 2. And instead of raising it to the n minus 1 power, we're just raising it to the n power in this particular case because we're starting at n equals 2. So that works. If we raise it to the nth power, this is 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power. So 2 raised to this power. That works. And it is geometric. All right, so that's going to be my denominator. Now that I have my denominator, I think, oh, well, what about that numerator? All right. That numerator is very perplexing. So just kind of studying it, looking at it, sometimes I like to look if there is a relationship between the numerator and the denominator. And it appears that there is. The numerator, every numerator is 1 less than the value in the denominator. So if the denominator is 2 to the n, the numerator could be expressed as 2 to the n minus 1. So the numerator, 2 to the n minus 1 all over 2 to the n. We do not have alternating numbers, so we don't have to worry about that. And there is how we come up with the formula. So these are tricky. You have to look for patterns. Look to see if there's a geometric pattern. Look to see if there's an arithmetic pattern. And then play with the numbers a little bit. Yes, you just have to kind of play with the numbers a little bit so that you can get it to work. Even though I saw that the denominator was geometric, and our normal geometric is 2 to the n minus 1. I saw that that didn't work, but I did see that if I got rid of the plus, the minus 1, 2 to the n did work, and that seemed to make perfect sense. Each denominator is just 2 to the n. So you have to play with the relationships a little bit until you get something that works. All right, hope you enjoyed the video. See you in class.